So in this chapter, we consider lenses and curved, spherical actually, mirrors. So we talk about convex lenses and concave lenses. All right. And we talk about convex mirrors and concave mirrors. So we talk about four things. 2 lenses, 2 mirrors. Concave, convex. Okay? And in all of these problems, the main task is the following. I have an object, and some distance away, I either put a lens or a mirror. So somewhere over here, it's either a lens or mirror. And there's something over here, a lens or mirror. And what I'm going to say is very, very important. It sounds like, well, of course, that's obvious. But it's going to be very, very important later on, as you'll see. In the case of lenses, right, we're thinking of a glass, plastic type of lens, transparent to light. So light is gonna, when you see this object, right, visible light is gonna hit the object. Light is gonna go in the direction of the lens or the mirror. And if it's a lens, the light is gonna go through the lens. Some of it is gonna get reflected, but when considering a lens, we are interested in the light that goes through the lens. Now, if it's a mirror, the light is going to hit the mirror and come back. So, I mean, it's kind of obvious, like, okay, it's going to hit the mirror and go back, so it's not going to, the light is never going to make it to the other side if this is a mirror. But if this is a lens, yeah, there will be some reflection, but minimums, but then most of the energy is going to go forward. So, if it's a lens, you'll have light on this side. If it's a mirror, you're not going to have light on that side, right? So here's the object, and here's some lens and some mirror. Now, what will happen is that whether this is a lens or mirror, the light is going to interact with the lens or mirror. And I say interact because for a lens, the light will go through, it'll refract. But for the mirror, the light is just going to bounce back, it'll just reflect. So the light will then reflect from the mirror or refract through the lens, or I can just say interact, keep it general for lenses and mirrors. And the light that goes through the lens or refracts or reflects from the mirror is going to form an image somewhere, an image of this object. And we want to know, where's the image going to be? How long, where is it in space? How far is it from this lens or mirror? Is the image inverted or is it upright? Is it enlarged or is it reduced? So that's the main task. Where is the image going to be formed by that lens or mirror? Yes? And this is very important. So, because this is where, what I'm going to say next is where people make a mistake. It's like the hardest part. I mean, from experience, right? Students is like, ooh, So, hear me out. It's important to remember, it's going to go through the lens, the light, but not through the mirror. It's going to reflect from the mirror. If this is the object, and that's the lens or mirror, right? Let's take one at a time. Let's say it's a lens. either convex or concave. I don't care. Let's just say let's just keep it general, right? If, remember, the light is going to go through the lens. If the image is formed over here, on this side, that's going to be formed by light that went through it, through the lens, and actually meet over there to form that image. So then that image is going to be real. That would be a real image. If, on the other hand, the light comes in, goes through the lens, and the light never forms an image on this side, because they just never cross somewhere over here to form the image, you get the impression that the image is formed on this side, where the light never made it to, because it's a lens, it went through. So if the image is on this side, the image is virtual. So an image can be real or virtual. So the way that I remember it is, if the image is real, it is because light rays after interacting with the lens, going through the lens, or after reflecting from the mirror. So the light rays that interacted with the lens or mirror after interacting with the lens or mirror, if the light rays actually crossed where they formed the image, then the image is real. If the light rays seem to cross where the image is formed, but they never really made it there, then it's virtual. Let me give you an example. You go to the restroom and you look at yourself in the mirror. What do you see behind the mirror? You. Right? But that's a flat mirror. The light from the lamps hits you, goes to the mirror, and you see an image on the other side. Did the light rays actually go over there to the other side to form that image?
No.
No, there's a wall over there, and then there's a hallway after that, right? So that person that you see over there is a virtual image, because the light rays never went there to form the image over there. It's just that the light hits you, goes to the mirror, and comes back to your eyes in exactly the same manner as if somebody was there and the light went to that person and came to you. Someone who's just like you, like a perfect twin. Yes? So what you see depends on how the light rays come into your eyes. So if the light rays come into my eyes after reflecting from the mirror in exactly the same angle and everything the same as if somebody was actually there and the light hit that person and came to you, then I'm going to see that person, even though there's nobody over there. So that's a virtual image. Well, it's virtual because the light rays never made it over there, because they never made it to that side of the mirror. Yes? So, for a lens, light comes over here, right? If the image is formed over here, it's because the light rays, after going through the lens, they cross to form that image. It's a real image. But the light rays go through the lens, but they don't form an image over there, but they seem to form an image over here. They seem to come from here. That's a virtual image. On the other hand, for a mirror, the light rays come in and they bounce back. If the image is formed on this side, it's a real image, because it was an image formed by light rays that reflected from the mirror and actually crossed over here. The light actually crossed and met to form that image over here. But on the other hand, if the light comes in over here, hits the mirror, goes back, but then it doesn't form an image over here, it seems like the light is coming from over here, then that image is virtual. So what we need to remember is this. So we're always going to start with the object on the left side, to the lens or mirror. If this is a lens, if the image is formed over here, it's a real image. But if the image is formed on this side, it's a virtual image. But if this is a mirror, if the image is formed over here, it's a virtual image, because the light rays never made it there. But if the image is formed over here, it's a real image. Yes, and I'll show you some diagrams, and then you'll see, oh, it's going to be this, oh, it's going to be that. But that's the biggest hurdle that students find. So, Y denotes the height of the object, and S is the distance from the object to the center of the either lens or mirror. That's S. So that's called the object distance, object height. And then let's say an image is formed over here. Let's just say there's an image formed over here like this. So Y prime is the height of the image. So this is the image. And the distance from the image to the center of this lens or mirror is the image distance. So this is the object distance from the object to the center of either the lens or the mirror, and this is the object height. You know, size of it. S prime is the image distance from the image to the lens or mirror, and Y prime is the height of the image. And we're only going to use basically the following formulas. A couple of formulas, pretty much. We're going to use 1 over something that has to do with the lens or mirror. It's called the focal length, equals 1 over the object distance plus 1 over the image distance. And there's another formula for the magnification of the lens or mirror. And the magnification, I'm going to write it over here, is defined as, the magnification is defined as the height of the image divided by the height of the object. If the magnification is 2, it means the image is twice as large as the object. Right? So it's defined as the height of the image divided by the height of the object. And this turns out to be equal from geometry and, reflection and refraction. That turns out to be equal to the negative of the image distance over the object distance. So there are advantages and disadvantages to this chapter or this topic. The advantage is that you pretty much only need 2 formulas, and they apply to all 4 cases. But obviously, a convex mirror is not the same as a concave mirror, and a convex lens is not the same thing as a concave lens. So what we need to do is discuss these 4 parameters. The focal length of each one of them, of the 4 things, the 2 lenses and the 2 mirrors. We gotta figure out, establish, when do we say that this focal length is positive and when is it negative. We have to establish when the object distance we write as positive in the formula and when we write it as negative. We have to figure out when the image distance is positive and when it's negative, and when the magnification is positive and when is it negative. All of these 4 cases. So there are 4 discussions that we need to have for all of these cases. The algebraic sign of F, the focal length, the algebraic sign of S, object distance, the algebraic sign of S prime, image distance, and the algebraic sign, plus or minus, of the magnification. It turns out that magnification and the object distance are the easiest. They're the easiest. F is not so bad. This is where people screw up. S prime. And S prime is positive if the image is real, which for a lens should be on that side, but for a mirror it should be on this side. Once you understand that, then it's a piece of cake. And S prime is negative if the image is virtual, which for a lens would be on this side, but for a mirror it would be on that side. If you just remember that for a lens the light goes through and for a mirror the light reflects, it makes it a lot easier. Okay, so that's, and then what we want to do when I discuss all of this is we want to consider, what if you put 2 lenses? What if you have an object here, and then you have a lens over here, and then another one over here, some distance away. Where's the final image going to be? And I would also like to consider what happens if, considering the eyeball, given, you know, like if you see pretty well objects that are nearby, but not so well on objects that are far away, can you correct your vision? What type of a lens would you prescribe? Well, it should be the focal length of that lens. And if it's gonna be a lens like this, which is like, I don't know, a centimeter or so, or 2 centimeters from the eyeball, or are you gonna be wearing a contact lens, which is right up against the eyeball, right? So how do you take that into account? So we wanna have that little discussion as well. So, but the main job is, where is the image gonna be when an object is in front of a lens or a curved mirror? And we only use 2 formulas, pretty simple. But we need to know when this is positive, when this is negative, when this is positive, when this is negative, when this is positive, when this is negative, when this is positive, when this is negative. So what I like to do is I start with one of those parameters and consider all 4 cases. Take care of that. And then I go to another parameter, consider all 4 cases. Done with that. And then another parameter, all 4 cases, you know, like that. That way we'll know at the end, right, for any of those cases, when f is positive, when f is negative. Okay? So that's basically what we're going to be doing in this chapter. Okay.